everyone, a warm welcome to the sixth part of the problems in wave equation. We got the solution of wave equation as y of xt is equal to sigma n1 to infinity sin n pi x by l into a n cos n pi ct by l plus b n sin n pi ct by l. We can find a n and b n by using the equations. A n is equal to 2 by l integral 0 to l fx sin n pi x by l dx, and Bn is given by 2 by n pi c integral 0 to L gx sin n pi x by L dx. Really, y of xt is the displacement at any point on the string at a distance x from the origin and at any time t. Next, we have to find y of xt when fx is given or gx is given or both are given. In our problems, fx and gx are either in terms of the trigonometric function sine or polynomials. In this video, I am going to solve a problem in which its initial velocity gx is given as a polynomial. Let me illustrate it.
Look at the question. A tightly stretched string with the fixed endpoints x equal to 0 and x equal to L is initially at rest in the equilibrium position. If each of its points is given a velocity lambda x into L minus x, find the displacement of the string at any point at a distance x from one end at any time. Say our one-dimensional wave equation is dou square y by dou t square is equal to c square dou square y by dou x square. Our boundary conditions are y of 0 t equal to 0. From the question, it is very clear length of the string is L. These two equations for validity. Next, we have to make the initial conditions. Initial conditions are depending on the initial position of the string and the initial velocity. See, from the question, you have to notice that the string is initially at rest in the equilibrium position. Say our string is in the equilibrium position. Say it is on the x-axis. See, on the x-axis x equal to 0. So our fx is 0. Or you keep in your mind, if the string is in the equilibrium position, so fx is 0. So y of x 0 is equal to fx. Since it is in the equilibrium position, it is 0. Next, regarding initial velocity, see, here the initial velocity is given as lambda x into L minus x. We have to find the displacement y of xt. We know the solution of the wave equation y of xt. It is c1 cos px plus c2 sin px into c3 cos cpt plus c4 sin cpt. That's equation number 1. We have to substitute these conditions in equation number 1 for getting the arbitrary constants c1, c2, c3, c4 and p. For substituting condition A, we have to write y of 0t. For getting y of 0t, you put x equal to 0. So, in the right side, you can see x is with the cos px and sin px only. There you have to put x equal to 0. So, it is c1. See, this term will be 1, so it is c1, and this term is 0, hence this term will be 0. So ultimately you can see it is c1 only. So c1 into c3 cos cpt plus c4 sin cpt. See, y0 t equal to 0 implies c1 into c3 cos cpt plus c4 sin cpt equal to 0. This implies c1 equal to 0. You put in equation number 1. We have y of xt is equal to c2 sin px into c3 cos cpt plus c4 sin cpt. That is equation number 2. Next, we have to substitute the condition y of ft equal to 0 in equation number 2. For that, we have to write y of, for getting y of lt, you put x equal to L. In equation number 2, You can say x is only with the sign px. So here you put x equal to n. So it is C2 sin pl, C3 cos cpt plus C4 sin cpt. See, y of lt equal to 0, which implies this equal to 0. That is C2 sin pl, C3 cos cpt plus C4 sin cpt equal to 0. Which implies C2 sin pl equal to 0 implies here C2 cannot be 0. If C2 is 0, from equation number 2 it is clear y of xt is 0. That is impossible. So the only possibility is sin pl equal to 0, which implies pl equal to n pi, which implies p is equal to n pi by l for n equal to 0, 1, 2, 3, etc. You put p equal to n pi by l in equation number 2. So 2 becomes y of xt is equal to, that is wherever you see p in equation number 2, you replace p by n pi by l. So if you see 2 sin n pi x by l, C3 cos c n pi t by l plus C4 sin c n pi t by l for n equal to 0, 1, 2, 3, etc. See, in this solution, you have to notice that when n equal to 0, y of xt is 0, which is impossible, as I already mentioned in the previous problems. So, n varies from 1, 2, 3, etc. See, for n equal to 1, we have a solution. For n equal to 2, we have another solution, etc. So, you can write the most general form of the solution by taking their sum. So, we can express y of xt as sigma n equal to 1 to infinity. Here, sin n pi x by is a common term. So, into see C2 to C3 is an arbitrary constant. Let it be a. It also depends on n. For that, you have to denote it by an. So, an cos Cn pi t by l plus similarly C2 into C4 is another arbitrary constant, depends on n, so we can write the arbitrary constant as Vn and sin Cn pi t by l. See, this is the most general form of the solution of the wave equation under these conditions. See, in this solution, we have two arbitrary constants which are an and bn. So our next aim is to find an and bn. In previous videos, I noticed the equation for getting the values of an and bn, and an is given by an is equal to 2 by l integral 0 to l fx sin n pi x by l, bn equal to 2 by c n pi integral 0 to l gx sin n pi x by l dx. You put condition C and D. Since fx is 0, we have a equal to 0. Here gx is this polynomial, so we have to find bn. Bn is Bn is 2 by Cn pi integral 0 to L. Gx is lambda x into L minus x sin n pi x by L dx. Next, for evaluating this product, we apply a shortcut method, and I already mentioned in the previous video. Let me explain the shortcut method with one example. You consider a single product integral x square minus x into sin x dx. See, you start with the polynomial. Here the polynomial is x square minus x. Assign alternating sign starting with the plus sign. So next sign is minus, then plus, etc. Like that. You write the successive derivative of this polynomial. Its derivative is 2x minus 1. Its derivative is 2. Next you consider the second function, which is our sin x. You write its integral here. Its integral is minus cos x. See, integral cos x is sin x and integral sin x is minus cos x. Next you write its integral here. It is minus sin x. Here you write its integral, that is cos x. See, the integration is over. Next you can combine the sign. That is, you adjust this sign here, so this polynomial becomes x minus x squared into cos x plus 2x minus 1 into sin x plus 2 cos x. See, this is the shortcut method and it is known as Bernoulli's equation. So here, see, in all these types of problems, you can avoid integration by parts. You take the constant outside, it is 2 lambda by c and pi, integral 0 to L. You open the bracket, it is xl minus x squared sin n pi x by L dx. See, it is 2 by lambda c n pi into, we have to apply the shortcut method. So, you have to notice that integral sin n pi x by L is minus cos n pi x by L by n pi by L. And again, integral cos n pi x by L dx is sin n pi x by L divided by n pi by L. We have to apply this result on the evaluation of this integral. You start with the polynomial. Here the polynomial is xl minus x squared. Your sign, alternating sign. You write its successive derivative. Here its derivative is L minus 2x. Here it is minus 2. Its derivative is minus 2. So at this time, don't simplify the sign. Next you have to write integral of this function here. And its integral is minus cos n pi x by L by n pi by L. Here minus sin n pi x by L by n square pi square by L square. Here it is cos n pi x by L by n cube pi cube by L cube. See, now integration is over. Next we have to simplify the signs. That is 2 lambda by c n pi into. You adjust the negative sign here, so the polynomial becomes x square minus xl into. Here it L by n pi cos n pi x by L plus n square by n square pi square. This will become n square by n square pi square minus into minus plus L minus 2x into sin n pi x by L minus 2L cube by n cube pi cube into cos n pi x by L. We have to apply the limit from 0 to L. And you have to remember sin n pi is 0. Cos n pi is minus 1 raised to n. So you put x equal to n. So 2 by lambda c n pi. So it is our bn. When x equal to n, here it becomes L square minus L square. So this term is 0. So completely this will be 0. Plus when x equal to n, here you can see sin n pi, which is 0. So this term is also 0. Minus when x equal to n, cos n pi, it has a non-zero value and is minus 1 raised to n. Minus of, next we have to apply the lower limit. When x equal to 0, this term is 0, so completely this will be 0. When x equal to 0, sin 0, so it is 0. 0 plus 0. So in the last term, cos term will be 1. So minus 2n cube by n cube by cube. This is equal to 2 lambda by c n pi. Here minus and minus plus. We wish to start with the positive term. So you write first term as this term, that is 2n cube by n cube pi cube minus 2n cube by n cube pi cube into minus 1 raised to n. So this is equal to, you can see 2n cube by n cube pi cube is a common factor, so you take it outside. So 1 minus minus 1 raised to n. And it is 4 lambda L cube by c n raised to 4 pi raised to 4 1 minus minus 1 raised to n. That is our required Bn. We have to substitute B in equation number 5. So y of x2 becomes sigma n equal to 1 to infinity. See, in this equation we notice n equal to 0. So this term is 0 and Bn is given by this one. So we can write 4 lambda L cube by c n raised to 4 pi raised to 4 into sine n pi x by L sine c n pi t by L. See, this summation we can take 4 lambda L cube by c pi raised to 4 outside. It's not necessary. Here sigma for n equal to 1 to infinity. So it depends on n. So 4 lambda L cube by c pi raised to 4 is a constant. This is the required displacement. Really, it is the displacement at any point on the string at a distance x from the